All right, folks, we're going to transition into assignment 17, which will be hopefully a review of the Cartesian coordinate system and functions. And so these next examples will go along with that. Just very quickly, the Cartesian coordinate system is named for a French mathematician named René Descartes. And so, again, take a look at the notes that were sent to you. Here's a picture of René Descartes. Here's a horse. You already know the punchline. Don't put Descartes before the horse. Ha ha ha. Okay, but anyway, René Descartes was a French mathematician and philosopher who basically developed this, this thing that we're about to take a look at. So, we have a two-variable equation up here on example number 1, negative 9x plus 5y equals 160. And the idea would be that both the x and the y could be replaced with numbers. So the thing that I'm very hopeful you're familiar with would be that when we give a solution to this type of equation, we need two numbers. We need a value of x, and we also need a value of y. And the mathematicians of the world decided that every one of these solutions would be called an ordered pair because it's two numbers, and it's in the order of x followed by y. So I'm going to buzz through this first page here. It should be easy for you. The idea would be that if somebody said, would you please complete the following ordered pair, you would say, well, this person gave me a number to plug in for x. So I'll take this equation and replace the x with 100. And y would be the unknown, wouldn't it? So it would be the variable at this point. And you could solve that now. So you would multiply this and get negative 900 plus 5y equals 160. Normally I'd be doing this together with you, but as you know, we're not together right now. So, and then you keep solving, right? And so it turns out that if you continue solving this, once you plug a number in for x, it's a one variable equation, isn't it? And so you would solve it like we did in the previous chapter, and in this case, you would say that when x is 100, y has to be 212 for that to work. So if you plug a number in for one variable, you can solve for the other, can't you? And it goes both ways. If you wanted, and I'm only going to probably have time to do one more of these. Again, what I would typically do in class would be I would have you work these out while I hand out papers. But in this instance, didn't we give you the y value? And so therefore, x would be the variable, and you would plug 32 in for y, right? When we give you the second number, we're giving you the value of y. So anyway, then you would solve here for x, and 5 times 32 is 160. And then you subtract over the 160. This is linear, isn't it? Linear, that's interesting. So then this would be 0, and then you divide the negative 9, and x turns out to equal 0, doesn't it? So the point is, if I give you a y, you can solve for x. Does that make sense? Okay. You know, this reminds me of the Valentine's Day card that I gave my lovely Helga here recently, where I said, you know, I was a y floating around aimlessly in search of an x, and you came along and completed my ordered pair. Isn't that romantic? But anyway, every x has a y, and every y has an x. Very romantic, isn't it? And so, I won't drag you through the remaining ones, but we could keep creating ordered pairs as long as we wanted, couldn't we? And this list would go on and on and on, and as a matter of fact, it already feels like it has. So, you know, in each of these cases, here you'd put 104 in for y and go about solving for x. And there again, those are things that we could have done together. Pause the video if you want and practice them. But if you put 104 in for y, you should get 40 for x. If you put in negative 5 for x and solve for y, you would get 23. If you were to put negative 4 in for y, solve for x, right? Every time you plug a number in for one variable, you can solve for the other. You get the idea, but that turns out to be negative 20. And then if you put in 37 for x, hit pause. Why don't you work that one out? Okay, you put 37 in for x, and solve for y. Hit pause, solve it. You can cheat, you can look at the next slide if you want. See, typically in class you wouldn't have that next slide. But anyway, if you put 37 in for x and solve, turns out to be 98.6. All right? And this is the point where I always ask people then, and all those ordered pairs are on that slide that you have in front of you. So you could have cheated and done them all. And look, this is where I would typically give away the punchline. But usually when you give that, it gives away the fact that every one of the x's in these ordered pairs would be a Celsius temperature, and the y's would be the corresponding Fahrenheit. And so, for example, that bottom ordered pair would be body temperature on the two scales. So on a Celsius scale, if you took a Celsius thermometer, your normal body temperature should be 37. That ordered pair is freezing, and that ordered pair is boiling. And then 104 Fahrenheit, which is 40 Celsius, means it's really hot outside. Nothing really particular about that. And then, of course, that would be, man, it's really cold outside. So then the discussion usually goes, how many different answers does this equation have? How many ordered pairs would satisfy this? And I would hope you'd say, well, you know, Mr. Solar Panel, I think there'd be like, you could keep extending this list, couldn't you? So the problem is, how do you list every answer when there's an infinite number of ordered pairs? So this is where our good friend Descartes comes along, our hero. Here's Cafe Descartes in Chicago. I made my children stop and take a picture of me in front of it, much to their embarrassment. But anyway, number lines have been around forever, and so we had a number line for x. You know, typically you think of 0 being kind of in the middle, all right? And Descartes came along and he says, and he was French, and he says, ho, ho, ho. You like that French? I need a beret. Sorry, I don't have one. I need a beret and a baguette and, I don't know, a bottle of wine maybe. Ho, ho, ho. We have a number line for x. And the thought was, what do we do about y? It needs its own number line. Y needs a number line, doesn't it? And it doesn't seem revolutionary now, but Descartes came along and said, ho, ho, ho. We would put the number line for y up and down. So x would be this way, and y would be this way. Ho, ho, ho. Okay, and that's called the Cartesian coordinate system. So then the idea would be that every one of these ordered pairs that we've listed so far is a location. I'm looking at the x's, and I kind of did this on purpose. The values of x, most of them seem to be multiples of 20 or close to multiples of 20. So the thought would be perhaps we could scale that by 20s. 20, 40, 60, 80, and 100. And then, as you know, negative numbers go this way. Now, what about the y? And by the way, this is called the x-axis. This is called the y-axis. So anyway, well, I'm looking at the y's, and you can pick any scale you want. I'm thinking maybe you could scale that by 50s. The point is they don't have to be the same scale. It just depends on the numbers that you encounter. So 50, 100, 1, so positive this way and negative this way, right? And there's that French Descartes guy, right? And I can tell you stories about Descartes. He and I went to high school together. Pretty good guy. But anyway, so the ordered pair 100, 212 would be 100 on the x and 212 on the y. And if you scan your eyes to where those would intersect, just like reading a map, wouldn't that be that location right there? So the idea is, the point I'm trying to make, that was kind of a pun, is that every one of these ordered pairs is going to be a point on a graph, a dot, an ordered pair. And the process of taking that ordered pair and bloop, putting that dot there is called plotting a point. All right, so I hope I made my point. 0, 32 0 on the x, 32 on the y, that would be approximately there. Okay. Let's see, 40 paired with 104, 40 on the x, 104 on the y, roughly there. Yeah, we're in the graphing chapter. Yay. All right. -5 on the x, 23 on the y. I'm eyeballing a little bit. -5 on the x, 23 on the y. That'd be about -5 on the x, 23 on the y. Maybe right about there. I hope what you're realizing is I could keep plotting these points, but we're starting to see a pattern here, aren't we? It turns out that if we continue plotting these ordered pairs, we will see that they're falling in line with each other, aren't they? All right? They're a little bit off because I was eyeballing things. But here's the point I always try to make to people is this. It is impossible to list every ordered pair that would solve this equation. So the best we can do is draw a picture. And if we keep plotting these ordered pairs, we're going to discover that they fall in line with each other. And if you keep going, there will be more this way. Put an arrow there, and there'll be more this way. And why would it be a line? Because look, first power. Haven't we talked about when your variable's to the first power? Linear, all right? Line. So when both variables, you have a two-variable equation, it's going to build a graph, x, y, two variables, and they're both to the first power, linear, line. So it was overkill to find all these ordered pairs. We only really needed two, didn't we? So yeah, we're in the graphing chapter. I've had people tell me, I hate graphing. That's fine. So my response is, if you don't want to draw a picture of the solutions, then list them all for me. Ha ha, you can't do that. It's impossible. It's infinite list. So there you go. We need to learn to love graphing. So that's everything I can think of as far as an introduction to the Cartesian coordinate system, and we'll move forward from there. So, ho ho ho. I need to work on my French accent, don't I?